This video provides a quick overview of several different ways of calculating a magnetic field, with an emphasis on the ones that are used in an introductory course. Because there are many different ways of calculating magnetic fields, the interpretation step is critical. You need to know how to pick the one to use, because that step is at least as important as knowing how to use each method correctly. I present them in the order of importance for an introductory course, but at the end I include some that we will never even use in this course. In fact, some of them are not even in our textbook. The ones towards the end are more general and thus more important if you go into advanced classes in physics or electrical engineering. In addition, some of the statements I make assume the fields are static, which is the situation at the start of this course. Okay, first, actually zero, is Gauss's law for magnetism. It says that the integral over a surface of B dot dA is zero. This is true because there are no observed magnetic charges, what we call magnetic monopoles. Until someone discovers them, this integral will be zero, with the result that the magnetic field does not ever diverge away from its source the way electric fields do. That means that magnetic fields circulate around in closed loops, like you see on the left, rather than diverge from a point like electric fields do. The circulation of a magnetic field is understood from what's called the right-hand rule. If you grab a wire with your right hand and your thumb is in the direction of the current, the magnetic fields form closed loops that circle around the wire in the direction that your fingers curl around the wire. Interpretation of the problem starts with noticing that it's a magnetic field that you seek, and if that's the case, your assessment has to ensure that the answer you get circulates around that source, circulates around the wire. The first instance is a long straight wire, the first thing we do in this course. In fact, you may have already watched the video about that particular problem. If we have a long straight wire, we can calculate the magnetic field at a distance r from a current using this formula mu naught I over 2 pi r k hat cross r hat, when that current I is flowing parallel to the z-axis described by that unit vector k hat. The cross product here is what you use for the most general case of the problem. That case and others are in a separate video. Here I'll just remind you that when you have a current flowing out of the screen, that is in the z direction, crossing k hat with r hat gives you a vector in the theta hat direction, which is a vector that circulates around the wire as I show you on the right side, so the magnetic field is always at right angles to that unit vector r. That means the magnetic field vectors are tangent to the circular field line that goes around the wire. And once again, that's given by the right-hand rule. And you should always assess your answer to be sure it obeys this particular rule. You should also follow a definite procedure when attacking each current source as a separate problem, just like you did when you did electric fields for separate charges. And I expect you to be able to do a case like this in any possible situation in terms of where the coordinate point is located relative to the wire. The second situation is where you have a current distribution with symmetry. So there's a distribution of the current, but it has a simple symmetry that allows us to use Ampere's law in its integral form, where you do an integral of the magnetic field around a closed loop, and that is determined by mu naught times the current enclosed. This is the third of Maxwell's equations. You might notice right offhand that it's got a structure that's rather similar to Gauss's law. That is, what's inside of that loop determines the magnetic field around that loop. This subject also gets its own video because it's the most common advanced method for calculating magnetic fields that you encounter in introductory classes, and thus it's important that you master it. It not only is similar to Gauss's law in some respects, it also shares the challenge that you need to learn how to apply it. The focus isn't so much on the equation itself, but on applying the equation to a particular problem. So, pay attention to each step in the IDEA approach that's in Strategy 26.1 and each of the examples in Section 26.8. Those examples cover basically every case that you might have to be able to do. Be sure you can explain the steps used to turn the integral of B dot dl around the loop into a simple product of B times L for each of the symmetries, and how to determine I encircled for each problem we might encounter. Please focus on the concept of enclosed or encircled and the critical thinking you need to use to determine the encircled current for any problem. This is the same challenge you had with Gauss's law, and you can actually use some of the Gauss's law thought processes, that is the critical thinking process, to attack these problems. Once again, I'll remind you, there's no formula for I enclosed. You get that by thinking. You must add up the currents inside of each Amperian loop of radius r and use that to calculate the field. Okay, now the next main method you encounter is superposition, which you've already seen for electric fields. The total field is actually the vector sum of the fields produced by each source. So if you've got more than one source, you identify each source of the magnetic field and use the right method for each one. Here's a simple example where there's a long wire shown in blue with a current flowing into the screen, and on the right side there's a current flowing out of the screen in a circular hollow conductor that would have to be attacked with Ampere's law. And here we want to find the field up on the y-axis. For the long wire, we just use the long wire technique. The dashed line shows the vector r, and you notice that the vector b1 is at right angles to r and in the right-hand rule direction, as you would expect for a current into the screen. The circular conductor also produces a magnetic field, but you have to calculate that from Ampere's law. Ampere's law will give you the magnitude, and from the symmetry and the right-hand rule, you can determine the direction vector as well. So we would get a vector b2 that is perpendicular to a radius vector. Now it's in the counterclockwise direction because the current is flowing out of the screen towards you. The final answer is found by adding those two vectors, just as we do for other problems with electric fields. Okay, so here I've actually used two different methods in a single problem. That's not so common in an introductory class like this one. In fact, it's pretty rare on exams in a class like this one, but it's not unusual in a junior or senior level course in physics, and of course quite common in real-world problems where you figure out a model for something and split it up into different kinds of things that you know how to calculate each of them separately. Okay, now I want to move on to some other methods which in general you're not as responsible for in this course because they use methods from particularly Calc 3 that most of you are either taking at the same time as this class. If we have an arbitrary current distribution, we can solve the problem by integrating over the distribution using something called the Biot-Savart law. This is a little bit like what we did with electric charges, but when we've got electric currents, it's a lot more tricky because the problem involves cross products. This is a method you'll find in advanced classes for physics and engineering majors, specifically electrical engineering majors. I'm not going to go into any detail because this also deserves its own separate video, but what you do is break the wire up into little pieces, and for each little segment of the wire you define a unit vector and a length, so that you get a dl vector that runs along the wire at that particular spot. And then you do dl cross r hat, much like you did k hat cross r hat. I'm sorry, k hat cross r vector actually, for the problem that we were doing with long wire. You're sort of like breaking up a long wire into little segments, but the formula is not as simple as you might think if you were to just go directly from the long wire formula. As I say, I'll treat this as its own separate topic. In general, this is an extremely messy problem. Even for the simplest situations, it's a messy problem because it requires skills from Calc 3 just to set up the integral and skills from Calc 2 to evaluate it. Because of that, I won't have you do any of them in this class. I'll show you the answers to some simple cases. The last one that we encounter in this course is with a time-varying electric field. It turns out an electric field can produce a magnetic field. It uses what's called Maxwell's displacement current in an additional term in Ampere's law that we don't see until much later in the course in Chapter 29. This is not a static field. In fact, the magnetic field only exists if the electric field is changing. So I mention it here for future reference. We won't see this for many weeks in the course. The situation is that even when there is no electrical current flowing, no current at all, no charges at all, if there's an electric field in a region and that electric field is changing with time, it'll produce a magnetic field that will circulate around that electric field region in closed loops. The key details here that I show in this particular picture is that you have to have an electric field that is changing with time, and I want you to notice that the magnetic field can exist in a region where the electric field is zero. Somehow that information flows from the region where the electric field is to where the magnetic field is created. This is critical to producing electromagnetic waves, so it's an essential topic, but it's one that's not introduced until we get close to when we want to look at electromagnetic waves. There's another way to do time-varying fields, and that uses Maxwell's equations written in a different way than you see them in our textbook. We use the integral form of the equations, which is the easiest to use in an introductory class, but not as powerful as if you write them in terms of vector operators. Because it uses vector operators, this method is well beyond Calc 3. You have to have taken Calc 3 and learned about these operators before you can even begin to learn about these techniques. The first one is the divergence of a magnetic field is 0. That says that it's not like electric fields. And the second one says the magnetic field curls around currents. Again, you don't know what these symbols mean in most cases, and even if you do know what they are, you realize we would need to know the electric field as a function of x, y, z, and t, and then solve what are actually partial differential equations to evaluate these. For that reason, they're not in our book, and they're well beyond the topics that we do in this course. But they are the ideal way to look at electromagnetic fields that are produced by currents in an antenna, for example. The last one I just mentioned for completeness, in fact, mainly just so that you know it exists. There's something called a vector potential and a scalar potential that are introduced in much more advanced classes, typically junior level classes for physics majors, but you usually don't really get serious about using it until you're in a junior, senior, or graduate level class for physics majors, and I imagine it's much the same for electrical engineers. If you're interested in the more advanced problems in electrical engineering involving electromagnetic waves or magnetic and electric fields, you would go explore these techniques. You not only need to know Calc 3 and partial differential equations, but you need to be fairly sophisticated in using those techniques. What the idea is like something like the potential that you have for electric fields, except it's now a vector potential, and you get the magnetic field by taking the curl of that vector potential A. It turns out that you can get that vector potential from an integral over a current distribution that is often simpler than the integral you would use for the Biot-Savart formula. That makes it an advantageous technique. And similarly, there's a scalar potential called phi star, which you can use to get the magnetic field from negative mu naught, the gradient operator applied to phi star. It turns out it's easy to get phi for magnetic dipoles, collections of magnetic dipoles, which makes it a useful technique for magnetic materials. Like if you're trying to design a magnet that will have a particular magnetic field, you can use this kind of technique to attack that problem. So again, I'll just end here.